So our next speaker, who's been a repeat speaker a few times, he has been a swim judge for the past 4 years. But until very recently, he didn't know how to swim. And he promised his wife that they would go on a coral reef swim session together. So he had to learn how to swim. So he learned, and they went swimming in coral reefs, and he's here to give us a talk about it. So everyone, please welcome Rafi.
All right. Thank you, everyone. My name is Rafael Lav. We'll get into it in a second. But before I start, what do you think this is? Anybody else? In about 5 minutes, you will know what this is and why this is important. A little bit about myself, Rafael Lav. I work at Deloitte. I lead data science for the public sector. I have a few roles around, specifically around cloud and Google. I work a lot in the NOAA space, IDO space, and really across state and local, really bringing AI, data science to the public citizens facing. The talk today is really not going to be about R or Python. I want to introduce really a new concept that is happening right now, kind of following Jared's conversation earlier, looking at a lot of maps. Let's take this one step forward into the world of Gen AI. So there will be not a whole lot of code over here, but there's going to be a little bit more conversation about what's out there and how you can start engaging with that. First couple of definition, I'll spend about 2 minutes really speaking to some information I would like you to understand to get the rest of the talk, and then we'll see some actual demos. So first of all, in the geospace, as we talk about maps and satellite imagery, etc., we're really talking about time first focus, meaning we really first looking even as we look across time, we look first as the pixel as across time, and then we add metadata, like information about it, weather, etc. So that's concept number one, is just across time. Second, just as an example of satellite imagery that we are using, all of you have access to these ones, Sentinel-2, for example. 2 satellites out there, they are taking imagery of a location, 13 bands, kind of an example of what bands are in the visual space on the bottom left over there. But what's really important over here is 2 things. One, they take an imagery roughly about every 5 days, so this is not immediately, and then there's some processing after that. And there are different bands and different resolution. You can see from 10 meters, 60 meters, that matter as we do geo analysis. An example of that, and here's, I cannot recommend the SITS package enough as you're really looking at the time series for geo data. You can see that vegetation, for example, I'm assuming everybody's seen a satellite imagery, but vegetation, you can really, again, talking about the bands that we talked before, you can calculate what is called over here NDVI index. You can see that on the bottom over here in the code, which is really a function of calculating differences between a variety of bands. And again, all of this is publicly available. Now, once we take all this data, 5 days apart, across time, we have this concept of data cube. Data cube is essentially where we take information, image collection across time, latitude, and time. And you can see that the problem that we are all facing is, as you can see on the top right over there, is that all of the imagery, not all created equal. There are storms, there are observability issues, clouds, etc. And there are other imagery that we deal with that separately, but you can see that the data cube is not clean. Like there's some area that cannot be used. Okay, so that's where we get to the concept. Now, how is that connected to AI? Embedding, I will make an assumption that we all kind of heard that term before, where we're really representing the information as vectors. And now, so you understand the pixel, you understand the data cube concept. Now we understand that you can take actually information and really embed that. And really where that's helpful is as we represent satellite imagery using an encoder-decoder system, and over here you can see, for example, in the Google world, they take 64 representations, and you can start taking all those bands for Centennial 2 across time and across the data cube and really start embedding that into vectors. Just as a idea over here, and you can see that when we start visualizing the embedding of Centennial 2, this is the same location, but different bands, etc. You can start looking at differently. Okay, so this was a GeoAnalysis 101 in roughly 3 minutes. Okay, why does that matter? Introducing Clay. There are roughly 142 foundation models. Foundation model like ChatGPT. Imagine a universe where we take all the information, visualization that we have around imagery, and we are going to embed all of that within the vectors. Essentially, we take the data cube, which is information across time, sampling that, embed that, and create a model. Clay is the largest one out there, and you can see that we really brought in, the foundation brought in a variety of data sets from Lancet, Centennial, etc., variety of bands and variety of meters representation, and really kind of turned it into a database of roughly 34 terabytes of imagery, roughly 70 million chips. Essentially, chips is like kilometer by kilometer. And now you have all this data embedded, which means Clay is essentially a computer vision model representative of the Earth, of all the data that we took from Centennial and other, converted into data cube, embedding, and really show that information across time. Now, all this data is already pre-trained, and now you have access to this information to do essentially 2 things or 3 things. You can do information retrieval, fine-tune, we'll get that in a second. But the real key over here, and this is where we come in, how do you access this information? How do you make this useful? How do you make this information that you got from this 200 million parameter, I believe that size right now? So it's not like ChatGPT size, but you can bring more information. Again, it's a foundation model. So couple words on Earth observation. So actually, what I will do right now, what I would like to do right now is before we get to Clay, I want to kind of represent this for a second. Let me just refresh that. So this is Alabama. Not very interesting as it stands right now, but let's change this for a second. As we change the color, you can see that the red one are houses or housing type. Obviously, vegetation is green, and then blue is water. But, and I'm going to use the mouse over here because it's very sensitive. You can see that every dot over here represents a visual over here. So here's some housing, here's some vegetation, again, within an area of the city. Obviously, this is water with a riverbank. So this is essentially a river. But there's some observation over here, see water in the middle of nowhere. Now, why am I showing you this? Because this is not Alabama. This is Alabama. So this is kind of the new way that we are looking at the world, not by where it is physically, but where it is next to something similar to this. So we just rearrange Alabama based on embedding that we just discussed 2 minutes ago. And now you have a lot of this information that essentially is by similarity. So again, if I'm looking specifically on an area within cities, so all these locations in the visual space or in the 2D space as they're next to each other, it's basically telling me that they are similar in some way, shape, or form where they are. Now, you can see that basically this is where the city is. You can see that these water are by themselves. Again, water by itself, but you can see that the water, for example, that sits over here All this water is a different type of water. It's water that is next to land, for example. Now, before somebody asks me why there is red next to the water, etc., again, it's by similarity. So if I bring, and again, this is just random, I'll choose one over here. You can see that the majority is built, but there is some water next to a bend. So it's kind of like in the embedding space, it's similar in nature. Okay, let's switch back over here for a second. So how do we turn this into an Earth observation, something that is useful? Now, you can start imagining that in the world of Earth observation, we can really convert all of this information into a useful data points or data usage that we can use. So for example, we can use this for site selection, right? This is a great example where we can say, hey, I have all this data, all this is similar. Find me all the location that I like that, like you just saw in Alabama. I'll show in a second. Mining is a illegal mining detection. Essentially, go show me all the location that of mine. I'll show you that in a second as well. So this is the world of Earth observation right now when we can actually get access to where things are. And what you can see is that basically we can take all this information and turn it into something useful. Which means, or in practice, what it means is that I can incorporate human feedback and fine-tune information to get information on deforestation, location of mine, flood detection, or any other area that we would like to detect just because it's similar to something that I already know that is about. So if you're familiar with ChatGPT, you can interact with that, but instead of a text, use an image, and I'll show you that in a second. So in practice, I can bring all this data on the right, and I can turn it into an information retrieval and fine-tuning. So I want to get information out, give me all the location like that, and then fine-tune that. And again, non-trivial, we're not going to get into specifically how to do this right now, but because it's a foundation model, imagine like the llamas of the world. All right, so I'm going to go through a couple. So what comes out of all of this is now I have a capability over here that is fine-tuned, that is already pre-trained, like Llama, like ChatGPT, and I want to use that information to actually get something useful. So we'll go through a few demos. The first one is I want to detect mining in Zambia. So how I'm going to do this? Right, I work for Deloitte. This represents my view, not one. Okay. So here's Zambia, for example. Now, a couple of things to note over here. So the information that you see over here right now on Earth, this is based on what's already Clay already have, or any other foundation model for that matter. So if you have access to foundation model, you can use that. So it's essentially already in memory. Now, what it really means that, as we talked about the data cube, not all the data is there, it's not always clean, etc. So we need to do some sampling, and you saw that we had 34 terabytes of information, but it's not everything. And I'll zoom in over here. The internet over here is a little slow, so it'll take a second to render. There you go. And you can see this is like, this is crop circles, is somewhere that exists already. Now, how do there are two problem statements that exist over there. First, I want to understand where do I have mine, and this is really important because some of them are legal, some of them are illegal, and then I want to understand what's the size of the change or size of operation they actually have, mostly because of health and taxation. Like they're being taxed on what it is. Now, the second part, the problem over here is I want to understand what are the artisan mining problems are. Couple of guys next to a village, go start digging, terrible for the economy, terrible for health. But it's also an area that we don't really want to send people into because it's kind of dangerous. So how do we manage and know what's going on? Now, in the good old days, this will mean satellite imagery. You blow this up, start looking, mark that. You spend 8 weeks doing this. I will do this live in front of you in 10 seconds. So what happens over here? We'll start by identifying a location that I already know. So you can see these are already been identified by an SME of a mine location. So this is known, and I'm going to run search. Now, behind the scene, you can see that it's running it at 90 at 90% similarity. And right now, because the information is already in memory, we just found these items. Now again, yellow, green is what I know about manually, that's my prompt. Yellow is what I didn't know about, and that's the new finding. Interesting to note, we actually confirmed that with a geologist, that those are what's called the mining belts of Zambia. So did a good job. It was actually very surprised. But what's really interesting now, I'm going to zoom in on one of them. Let's choose this guy. And what you can see over here is now where you can use something like a UI, and this is, again, outside of R and Python. This is more of a UI interaction, but you can see that over here I have a mine, and you can see this is 2020. Let's look at 2021. You can see there's a growth over here and here. 2022, growth over here. So now you can make a determination, hey, do I need to send somebody over there? Do I need to evaluate? Imagine in the world of the NGA, imagine in the world of other agencies, that we want to understand where do we need to spend our time to actually investigate. So in the NGA world, they would spend a day just figuring out where to look, but using tools like that, you can spend 30 seconds and now decide, is it worth my time to kind of look? And then you look at the place that you actually want to look. Just a side note over here, you can see, let's take this guy. I'll zoom on one of them. Let's zoom on the one in the middle randomly. And again, it will take a second to render. This needs a faster internet. You can see over here that there is what appears to be an artisan mining. It's relatively big, but you can see next to all the fields. And now you can evaluate, hey, is this something that I should be concerned about at the Zambia level, at the state level, or do I need to look at it from or is it okay? Now, oops, sorry. You can start looking at this from, for example, for coastal area that was, let's say, UNIFEMA or NOAA. You want to understand a location. Hey, this was impacted. Find me all the other locations that are like that were not impacted, and I can do something about it before it was impacted. So this is a use case that you can use. I'll use the rest of my time to actually speak to, okay, this was great. You build UI. How do I actually use this right now? I'm on my laptop. I don't have, $500,000 to build a cool UI. It's not $500,000, but I don't have the money. I want to build something really interesting. Now, all of this can be installed it does need a cloud environment, GCP in this example over here. But really what I want to point over here is that you need to kind of connect to the right data sources. So for example, the information that comes from the Clay Foundation, that comes from GitHub. We have data that comes from Centennial. And then the really interesting part is once this is running, you can really set an endpoint. And at that point, it becomes an API call. So here's an example. We can bring in massive amount of data, and you can see essentially what happens over here is the information, the new information. I'll show you an example in a second. I can bring new information in, foundation model. I can bring new information, and you can start looking at this from evaluate the data that you have, and then run it again very easily. And again, this is a Python in this case, to really kind of export out new location. So let me show you an example that there is over here, a couple of examples. Here's, for example, a fire that happens in Portugal. This is essentially the locations that where the fire happened. And now I can start seeing the before and after. So this is the forest fire, before and after, the location. I can find all of them. But even more interesting over here, I can actually start bringing in new data. So let me actually show you an example of this running. Can you guys? So it's a little bit of a code. I'm going to run it at 2.5. Essentially what's happening right now, and this is kind of where I want to finish over here. This is now becoming a little bit more accessible to the masses. Now, non-trivial, we invested a lot of time in figuring out how to do this. But once you figure out, and please feel free to reach out afterwards, you can see that I'm bringing now, and this is live, I mean, it's recording in live. We brought in the clay information. We bring that in. We're bringing in, now we want to really understand where are all the oil fields in New Mexico. So what we did right now is we brought in 1,250 new imagery from Centennial from July, this July. So even though clay is old, we can bring, because it's foundation model, we can bring in new information. And what's happening right now is I found one location over here. There's a few locations that I know manually. That's my prompt. And what I can do right now, and here, again, this is kind of like the location. And now I can run through the process of embedding all of this, bringing the actual imagery over here. You can see that over there. And once I have the actual imagery, I can now find the top and similar location based on that. And I'll finish by showing this. So the red is the one that we actually started with. And you can see all this in your notebook in Leaflet. And I will now find two locations that are of interest. So here's one of them. I think the second one is a little bit clearer. Yeah, it will bring this one up. And here is a location that we just found that is very similar to the one that we just started with that we didn't know about before, that there is some oil operation that we already know based on data from July. I'll just finish by saying, again, this type of work with a foundation model is where the geospatial, kind of where we all moving into. We don't longer just look at maps, but we look at embedding. Thank you very much for your time.